Here we have an example sequence of operations. A simple series of register transfer instructions are given here. R3 receiving the content of the memory at the address R0, and then the content of R3 is incremented by 1, and then in the memory we write the content of R3 into the same address from which we just started. So this means that we are just incrementing the content of the memory at the address of R0. Okay, but in order to do that, since the ALU doesn't have direct access into the memory, at the first step we need to read from the memory the content of the memory at that address, then increment it in the ALU, and then we need to write the result back into the memory. Over here you can see how the transfers are done. In order to perform R3 receiving the content of the memory at the address R0, first we need to provide proper value for the address of the memory, for the address input of the memory. It comes from A data, and therefore since we are going to refer to R0, which contains the desired address for us, we need to have AA equal to 00. When we have AA equal to 00, it means that at A data we have R0, and R0 is used as the address input of the RAM. We are going to read from the memory, so memory write should be equal to 0. And then we want to transfer this data. So once we have this over here at out, we have R0. We want to write this into R3. As a result, for MD, for the multiplexer that we have here, we will have 1 as the select value. Therefore, this MR0 data will be available at the output of the multiplexer here, and then it will be at the D data input of the register file. We want to write it into R3, therefore the D address here should be equal to 11. When this is the case, the D address is indeed equal to R3, and then since we want to write it into the register file, we need to have WR or write command equal to 1. Once this is the case, the operation is performed. You can also see here that the ALU in this case is not used, so we didn't use the ALU, and therefore the control commands for FS would be don't care, and similarly whatever we had for BA would be don't care as well. Then we need to perform the incrementing of the value of the content of R3 that we had, R3 plus 1. So this time A data needs to give us R3. In order to have that, we need to have AA equal to 1. If AA is equal to 1, then R3 will be provided here, will be available here. We are going to perform the incrementing of the content, so FS will be equal to 0001. And once that is the case, for F will be equal to R3 plus 1. We need to pass this to our register file, the result of the operation. Therefore, MD will be equal to 0, such that this will be the pass for our data to flow, and then it will be available here. And as a result, over here we will have R3 plus 1. We want to write it back into R3. Therefore, the A address here will be also 11 again. R3 is selected here, and then setting write to 1 will result in writing of the operation into the result of the operation into R3, or R3 will receive R3 plus 1, as you can see here. Something important to keep in mind is that MW, memory write, is set to 0 in order to prevent writing of data in any address of the memory that we something that we don't want to have, yeah, unintentionally. And B address is not used over here, so it is don't care. And then we need to write down the content of R3 back into the memory at the address of R0. So R3 is the data that we want to write, and as a result, B address this time will be equal to 1, 1. So at the B data line, we will have R3 available. And since we want to write it into the address in the memory with the value which is stored at R0, we need to have AA equal to 0, 0, such that at A data we have R0. So R0 is at the address input, R3 is at the data input of the memory. If we make MW equal to 1, memory write equal to 1, then the data that at R3 will be written into the memory address which we defined with the register R0. Now you can see that the ALU is not used, so function unit was ignored and we didn't care about that. And MD is also not important over here. Write WR is equal to 0 because we are not going to write into the register file, and therefore DA is not used, MD is not used, and FS is not used in this case. We can also pass the constant input. This is something that we already had in our Datapath design. We just need to introduce this multiplexer over here on the path of the B data. Then depending on the value of MB, whether it is equal to 0 or 1, one of the signals that we have here, the B data or the constant value will be selected, and therefore, since it's also available at the data input of the memory, we can also write that constant input into the RAM as well. This would also be useful when you want to clear the content of the RAM. Yeah, we can have the constant value equal to 0, and then if we set MB equal to 1, then 0 will appear at the data input of the RAM, and then we can kind of scan all the content, all the elements of the memory in order to write them with the value that we have here, which is 0, and then we just clean the whole RAM easily, okay, over a given number of clock pulses.